It's my pleasure to introduce our speaker this morning, Emmanuel Candace. So he's a professor of mathematics and statistics at Stanford University. He received a BSc from École Polytechnique in 1993 and a PhD from Stanford in 1998. He was a professor of applied and computational math at Caltech and returned to Stanford in 2009. He is a pioneer in the field of compressed sensing and won the 2006 Alan T. Waterman Award from NSF for his research. We're very fortunate to have him as a speaker today, and he will talk on information theory of data matrices. Yeah, one is for the speakers and one is for the recording. These two on.
Okay, so the computer doesn't wake up. What do I have to do? No. Okay, maybe that's not good. Really?
Just keep pressing. Shut down. Wake up. It does it too.
Is something happening, or?
I think let's see. This should turn off.
So it got me thinking, and so while the thing is going on, I'll give you a joke about math. All right, so there's this guy, and he doesn't know math, and he's from Armenia. And I don't know if you know that joke. He's from Armenia, and he goes around and studies math. And so he comes back to his advisors, and he says, I don't know why I did not know that so much mathematics was of Armenian origin. And his advisor looks at him and says, what? Is it of Armenian origin? And says, yeah, look at all these people, Hamiltonian, Slepian, Jacobian. Lambertian. Okay. Newtonian. You get it, okay. Okay, all right, okay. Okay, so here we go. Except you don't see my screen.
We're almost here. Yeah, so go to... Okay, so you want mirroring? Yeah, just do mirror display.
Okay, all right. Okay, so I'd like to thank the organizers for inviting me to speak. It's a wonderful event, and I would like to start with a few comments about the topic of this talk and perhaps about myself even. As you'll see, I'm a kind of a strange speaker because for two reasons. Number one, the word Shannon does not appear in the title. Number two, I promise I'm the only speaker without a picture of Shannon in my talk. And so I'm a bit different in the sense that perhaps I'm not a core information theorist, in the sense that my research is not preoccupied by calculating capacities, but I believe that most of my research has to do with information theory broadly defined. And I will try to expose you to perhaps other aspects of information theory, especially those aspects which combine information theories, theoretical ideas with statistical ideas. Another reason why the talk is a bit different from what you've seen, besides that most of what you'll see does not draw on a magical 1948 paper, is that most of what I'm going to present is fairly new. And so it's a new topic. And so, of course, it's not as well polished and developed as most of the things you're hearing about at this summer school. But I'm hoping that perhaps some of you who are looking for thesis topics and don't really know what to do during their PhD might find some interesting things in there. And since it's an emerging field, this field of recovering large data matrices from what appear to be incomplete and highly corrupted subset of entries or general linear functionals, that some of you might find this topic interesting and think about exploring some of these ideas in a thesis project. Okay. All right, so I will try to kind of tell you a little bit why this has to do with information theory. And so we're going to look at three problems. And they're kind of ordered in order of difficulty, not only of mathematical difficulty, but also on information theoretic difficulty in a sense that we're going to make precise later. The first problem is kind of an interesting problem. And it goes like this. You've got a large data matrix of interest. Unfortunately, you cannot collect all the entries of this data matrix. You can only collect a few. And so this is roughly indicated on this here by showing you that some entries have been collected, indicated by a blue cross, and some entries are missing, indicated by a question mark. And the question is, given that you see only a few samples of a large data matrix, can you reliably predict the samples you have not seen? Okay, and it seems like a very information theoretic question. Okay, in a way, if we go back to Shannon's, of course, it's very different from what Shannon did, but it's kind of what we're looking for here. It's kind of a sampling theorem, which is I have a large data matrix. I can only afford to sample it a few times. Then how many samples should I take to actually recover this matrix reliably? Okay, so let's think about the first question as a sampling theorem. And the question is, can I recover a data matrix from a few sampled entries? And of course, it looks impossible unless we're making some assumptions, which we'll do in a minute. The second question is in the spirit of error correction. And I'll try to explain that these problems come up in a gigantic number of applications. And the problem is this. Well, I have entries that have been recorded about a large data matrix, but many of them are bad. They have nothing to do with the original data I was interested in. Okay, so there are some entries that have been correctly recorded, and then there are some entries that have been incorrectly recorded, perhaps maliciously, perhaps sensor failed, perhaps many things happen. And so in this data matrix, I get to see everything, but a large fraction of these entries actually have nothing to do with the values that I'm interested in. Okay, and the question is, given that you see all the entries of a matrix, a fraction of which are corruptions, a fraction of which are good data points, can we actually recover all the entries of this matrix? Okay, so the first example, we're missing entries. So this can think about erasures in the information theory literature. Here it's really what we're looking for is some kind of an error correcting code for matrices where some of the entries have been badly corrupted. And of course, you can put the two together, which is what happens most often in the applications I'm interested in, which is you observe samples of a matrix. Many samples are not unobserved because you can't see everything. Some of these samples are badly corrupted, yet can you recover the matrix in the presence of large amounts of missing information and large amounts of corruptions. All right, okay. And now, because I'm slightly practically minded, I just don't want to do this by algorithms that take exponential amount of time. I would like to be able to do this, to answer these questions using computationally tractable algorithms, if at all possible. All right. Okay, so why do we care about this? We care about this because, and that's how I started to work in this area, and this area is growing rapidly, and I'll try to mention a few people working in this area. I started to work on this because, as Tracy said a few years ago, I was a professor at Caltech, and I lived in Westwood, so I had a long commute. And I would listen to NPR, which I don't do anymore, and that's a shame. And then on NPR, they were talking about the Netflix challenge, and I got interested in that. So the Netflix challenge, I'm sure that most of the students based in the US know what this is, but since I think we have lots of international students, let me explain what the Netflix prize is. So Netflix is a company that is renting out movies, right? So for those of you not in the US, basically you're a subscriber to a service. Through the web interface, you send movie titles that you would like to rent, and then you receive them through the mail. And then you watch them, and then you return them, and then you say, now I'd like to see The Godfather, and The Godfather is mailed to you, you watch it, you return it, and so on. Okay. Now, after you watch movies, Netflix will actually send you an email saying, how did you like this movie? Please rate it for me. Okay? And so what Netflix is doing is Netflix is assembling a very large database where the rows of this data matrix are users and the columns are movies. And people would rate movies. But the problem is that people rate on average, I believe in the Netflix matrix, about 50 to 100 movies, whereas Netflix is renting 18,000 titles. And so people would enter ratings, but of course this matrix is very sparsely sampled for the reason I just explained, that people would just typically rate very few movies. Now the challenge that Netflix has issued to the statistical, the CS, the IT community is, can you complete this matrix? And what that means is, can you actually predict ratings for movies that you have not yet seen? Okay, so you see samples of a large data matrix, and what Netflix is interested in is, of course, predicting the missing entries, predicting the movies that you have not yet seen, and they want to do this for obvious reasons, which are profit, because then, of course, they will be able to recommend titles you might like to see, and so then they can generate profits. Of course, you can imagine that Netflix is not the only company interested in these problems. Anything that has to do with recommendation systems, we are proliferating online, have exactly the same problem. If you're Amazon and selling books, if you're Apple and selling music, you all have the same problem. You would like to be able to recommend things that users might like to buy. Even Facebook has enormous problems like this. And so, you know, in the old days, you would go in a bookshop, and the bookkeeper would do a good job at assembling the books on the table so that, you know, books you might be interested in you purchase. But now it seems that we don't go to bookstores anymore. Even at Caltech, they closed a bookstore, which I think is a shame. And now you have to just essentially do the display online, and you have to do this by a recommendation system. And so that it is a very important problem in modern economy. Okay, so the fundamental problem that this raises, thinking a little bit as wearing an IT hat, is can we recover a data matrix M from a number of sampled entries, which is much smaller than the product of the dimension? And of course, in general, everybody would agree that this is impossible. And rightly so. For example, if the matrix has IID entries, there's nothing I can do. In this lecture, we'll come with some surprises that we'll see that we can recover matrices of enormous interest from incomplete entries. We're going to see that we can do this by convex programming, which is a real surprise, in my opinion. And then we're going to see that this can be made extremely robust. That is, that even though I see only a few entries, even though a fraction of them are corrupted in a possibly adversarial way, we're going to see that this doesn't matter, that I can still recover the structure of interest. Okay. All right. So the agenda for the talk has two parts. So in the first lecture, we're going to look at the sampling theorem of data matrices. And this second part, we're going to look at the error correction of data matrices. So the first part, we're going to talk about recovering a matrix from many missing entries. And in the second part, we're going to talk about recovering a matrix from missing and corrupted entries. Okay. So the first part is work that began with my postdoc, Benjamin Recht, and then that I continued with Terence Tao. I'm going to try to start this first part by introducing additional motivation and applications of this problem. And we're going to study the information theoretical aspects of this problem, and then the practical aspects. Okay, because this is a bit maybe outside of your comfort zone, I think it would be good if you interrupt me if something is not clear. Now, I assume that everybody knows what is a singular value decomposition. Am I correct? Well, that's perfect, because last night I was scared. Like if I said, if they don't know this SVD, then I'm in big trouble. Okay, but that's great. Which, as an outsider, I have to tell you that when I look at the information theory society from the outside, I see two things. I see great intellectuals, and I see a very well-behaved society. And so you proved point number one. It's because you know so much about linear algebra. You're intellectually highly capable. Okay, which is not the case of all societies. I mean, I also go to applied math conferences, and I can tell you that the applied math community has a lot to envy to the IT community because we're not as well behaved. I can give some examples, but without the video camera. But it's really something to go to an IT meeting and see this sense of family that there is. It's something that is a real treasure, I believe. Okay. All right. Okay, so let's talk about motivation and applications. Okay, so here's another problem that I find very interesting, personally, and it's connected to some of the stuff we heard yesterday. So it's global positioning from local distances. So let's say that we have a sensor network, and we have sensors going around, and they have locations xj in d-dimensional space. We can think about d as being 2 or 3. And what we can collect is sensors can talk to each other to some extent, and so we can try to get information about partial distances. That is, we would like to gather information between sensor number I and sensor number j. But the problem is tricky because let's say we have a sensor net where power is an issue, and so sensors can actually construct a distance estimate to their nearest neighbors, but not to sensors that are far away. Okay, so we have a low-powered wireless network, for example. And so each sensor can actually construct a reliable estimate to its neighbors, but not to sensors that are far away, which means that in this matrix of pairwise distances, I can only observe a few entries corresponding to sensors that are close by. And my problem here is to locate these sensors. Okay, so what I would like to do here is I would like to know where these sensors are. Of course, if I knew where they are, I could construct all distances. And it's almost a converse. That is, if I knew all pairwise distances, I could locate the sensor up to a rigid transformation. And so the problem is really a matrix completion problem where you observe local distances. That is, you observe a small number of entries in this data matrix, and you would like to guess all the entries because that is nearly equivalent to being able to locate all these sensors. Okay, of course, you can actually take my model and extend it, and I want to tell you that this field of matrix completion is a rapidly growing field, a bit like what compressed sensing used to be in 2006, 2005. And then, of course, you could have other types of measurements about data matrices. Instead of revealing entries of a matrix, you could actually observe inner product between a matrix and another matrix. That is, you have the usual inner products for matrices. And so a piece of information might come in the form of, the inner product between the matrix you're interested in and this matrix is this. But of course, we are in a setup where we would take as far fewer functionals than the total number of entries. And so we have, again, an underdetermined system of equations to solve. And the case of matrix completion is, of course, a case where the matrix AJ is a matrix full of 0 except 1 in a location, which means that when I take the inner product, I reveal this location. Okay, and so the field has extended most of the result that I will be discussing today to this case, and that's very important because of a lot of applications. And so one of the good things about working in this field is that every day you discover a new application. So here's an application which you'd be surprised to learn that people are actually doing physical experiments based on these ideas in Germany. And so the problem is the following. So in quantum mechanics, people would like to prepare quantum states, okay, to do experiments, to do various kinds of things. But then there's a basic question, which is once you prepare the quantum states, how do you know that what you prepared is what you wanted to prepare? So you have to measure it to make sure that what you prepare is what you thought you prepared. The problem in quantum mechanics is once you measure something, as I'm sure you know, you destroy the state of the system. And so what that means is you have to prepare many copies of the same quantum state systems to be able to know what you prepared. So quantum mechanically, and I'm going to not give you any details, I just want to give you a flavor of an application of matrix completion. Quantum mechanically, we can think about a k-spin 1/2 system in an unknown quantum states as being represented by its density matrix. And all you need to know is that the density matrix is a positive semi-definite matrix whose trace is 1 and whose dimension, whose number of rows and columns, is a square matrix, of course, because it's symmetric, positive, definite, is exponential in the number of particles. So it's a matrix of a very large dimension. And now we can sense this system by actually hitting the matrix against what quantum mechanics people call observables. And each measurement, I mean the average of measurement, is essentially giving you the inner product between an observable, which I'm calling AJ here, and the system M. And in quantum mechanics, people usually use these tensor Pauli matrices. And so they're exactly making linear measurements about a quantum state. But of course, because this quantum state is n by n, that is, you have to make an enormous number of measurements to know what this quantum state might be. And so the question is, can you actually reduce the number of measurements? Can you actually make far fewer measurements and still reliably determine what your quantum state is? Okay, and so what the question is asking is, can you undersample the number of measurements that you would naively take about an n by n symmetric matrix to reduce the number of measurements? And there's great theory about this that has been developed, and people are starting to make experiments to test these ideas experimentally. Another problem where you collect partial information about a matrix is in linear system identification. And as you can see, what I'm trying to show you is that the span of fields that are concerned with recovery of matrices from undersampled data is vast. And so in linear system, okay, all right. It feels a bit weird, but okay, no, not this one. Okay, so in system identification, you have a dynamical system indicated by x of t, and this system obeys this dynamics. Xt plus 1 is a matrix A times xt plus BUT, where U is an input. That's what you can actuate. Unfortunately, you don't observe this state. It's kind of a Kalman filter setup, if you like. You observe Y, which is a function of the state plus the input, and all these matrices A, B, C, and D are unknown to you. And so U is the input, that's the controller. Y is the output, that's what you can observe. X is a state vector, but you don't get to see it. And in system identification, basically all what you get to see is U, of course, what you put in, and Y. And what you want to know? Everything else. You want to know the system order X, that is a dimension of the state space. You want to know the dynamics of the system, that is a matrix A, B, C, and D. from simply the observation about y. And so if you think about it for a minute, what you're collecting is you're collecting linear functionals about these matrices. And so very quickly, it becomes a matrix completion problem as well. OK, so there are many other applications of matrix completion, of recovering a large data matrix from few linear functionals or few entries. My colleague, P.P. Vaidyanathan at Caltech, is looking at problems where you partially observed a covariance matrix, again motivated by problems in sensor networks where power is a limitation, which you can actually only cross-correlate signals from nearby sensors. In machine learning, these problems come up all the time. In computer vision, they come up. And so there are lots of problems of this nature. OK. All right. So now that I try to explain why these are important problems, I would like to kind of develop some theory for recovering matrices from incomplete entries. OK, so the problem we've stated is very simple. I see a few entries of a large data matrix. I observe a subset. Can we guess the missing entries? And of course, in general, I can't. Now, when you look at data that we care about, whether there are images on the web, whether there are videos, text data, web data, and so on. Yes, so these data, using a statistical language, are high-dimensional in the sense that I have many columns or many rows. But usually, these data hide a low-dimensional structure. OK, and so my point is that we're going to have to be able to say something useful about the sampling of data matrices, we're going to have to make a structural assumption about the data matrix, just like Shannon made a structural assumption about the kind of analog signal that we could sample, namely that they're band limited. Here, we're going to make a structural assumption, and the structural assumption is that those data matrices have low rank or are approximately low rank. OK, so everybody knows what is the rank of a matrix, obviously. Right. So we're going to make an assumption, and it's not a naive assumption. That is, it's an assumption that within practice, we're going to assume that the matrix that we wish to recover from a few entries has low rank or approximately low rank. And it is true of the Netflix data matrix. So if you talk to Netflix engineers, they will tell you that the Netflix matrix has rank no more than 100. In fact, I think it's much smaller. And since I would like to keep this a bit informal, I mean, do you know why the Netflix matrix has small rank? Of course, preferences are extremely correlated. People have very similar interests. And so this is an indication that the matrix has low rank, because if you look at the ratings for Goodfellas and if you look at the rating for The Godfather, they're going to be very, very correlated.
So if there is a low number of features that people look at movies,
yes,
but could it be that the features in the so I rate movies if Tom Cruise is in the movie. So there's like
by the way, this is the first predictor of whether you're going to like a movie. There are two kinds of people who like movies with big stars and people who like movies with no big stars. Right. And the first principal component, if you know what I'm talking about, the best predictor you have to know whether you're going to like a movie or not is exactly what you just said. Is there a big star in it?
Okay. so the low rankness, the low rank condition captures that in all cases. If there is a low, or is it possible that there is a low dimensional manifold that is non-linear?
It is possible. It is possible, but really, there are only a few factors that determine your preference for movies. And yeah, what you're saying is perhaps there's even a manifold of smaller dimension. What I'm saying is, but it may not be linear. But I'm saying, if you take a linear manifold of dimension 100, you capture 99.9% of the variation of this data matrix. That is, what I'm saying is that the 100th singular value of the Netflix matrix is so tiny that it's irrelevant. Okay? And in fact, for those of you who know, Netflix offered $1 million to a team that could predict ratings using a small mean squared error, improving the Netflix algorithm by 10%. And this was a Netflix prize, which is the best way I know of getting 1 million engineering hours for 10 cents an hour, essentially. And there was a team from the Bell Labs that won the competition using explicitly in the model that the matrix has low rank. In fact, trying to find a factorization of a low rank factorization of the Netflix matrix. Okay, so the Netflix matrix has low rank. The center net matrix is interesting because it has rank which is extremely small. If the sensors are in the plane, the rank is 2. If the sensors are in space, the rank is 3, and so on and so forth. The quantum state tomography, so if you prepare a pure state, the rank is 1. If you prepare a mixed state, but not a crazy mixed state, the rank will be very low. So these quantum state matrices have approximately very low rank. In control, the rank is the system order, which is typically low. And all the problems I care about, the rank is small. So you can compress something and make a structural assumption that the signal is sparse. It makes no sense to assume that a matrix is sparse here. What it makes sense is that it's captured by a few factors, which is a low rank assumption. Okay, so low rank matrices, it's interesting to think about low rank matrices by their singular value decomposition. And so if I have an n1 by n2 matrix, I can, of rank R, I can think about via its SVD, U sigma V star, which is something that Andrea discussed yesterday. And so U is the left singular vectors, V are the right singular vectors, and on the diagonal of sigma, you see the singular values. And when we write down the singular value decomposition, what we notice is we notice that the number of degrees of freedom in a matrix of rank R is much smaller than the dimension. Because if, and now let's think about this as an information theoretic person, if you want to send me a matrix of rank R, how many numbers do you need to send me? Well, you need to send me the U, the sigma, and the V star. And just by eyeballing, we see that the number of numbers you need to send me is much smaller than the total number of entries. So how many degrees of freedom does a matrix of rank R has? Well, I need to send you this matrix U, which has n1 rows and R columns. That's about n1 R numbers. I need to send you this matrix V. That's n2 R numbers. I need to give you the R singular values. That's R scalars. But because you have orthogonality conditions and so on, the number of degrees of freedom you can calculate carefully is the sum of the dimension minus the rank times the rank. So what does this mean? It means that if we have a matrix which is 1 million by 1 million, for example, of rank 10, its number of degrees of freedom is 20 million. It is certainly not 1 trillion. Okay, so the number of degrees of freedom in a matrix of rank R is much smaller than the ambient dimension. And so this begs the question, which is, now that I know that I'm trying to recover an object that has a number of degrees of freedom which is small, do I need to see all the entries to guess a matrix of rank R? Okay, and what I'm going to try to explain, it's not as an easy question as it sounds. Okay, so here is a matrix of rank 1. So that's should be an easy candidate and not a very complex object to recover from entries. So this is a matrix of rank 1. Okay, so it's the first basis vector times the last transpose. And so it's a matrix full of zeros and has a 1 in some corner. And I claim that a matrix like this cannot be recovered from a sampling set. So if you are kind enough to show me 50% of the entries, which are not the kind of numbers we would like to talk about, I mean, in Netflix, it's like 0.5% of what you get to see or something of that nature. If you show me 1% of the entries or 10% of the entries, 90% of the time I'm going to see zeros, of course, and there's no way I can recover this matrix. So matrices like this are completely out of the scope of what is possible. You cannot sample matrices like this in any way that I would know of and hope for low mean squared error. It's just not possible. Of course, this matrix is very peculiar. In the Netflix case, that would mean that the Netflix matrix, there's one user, Alex, who likes one movie, The Godfather, but no other movies, and all of us, we like absolutely nothing. Right? That would be... Or in the sensor net case, it means that all the sensors are at the same location and one is very far away. Okay, so these are very peculiar matrices that we do not care about. Another thing that you have to be a bit careful about is what do I decide to reveal? Okay, and so you can give me a very nice rank 1 matrix, a matrix of the form xy star. So the entries, the values of the entries is xi times yj. And of course, I can show you all of there is to see in this matrix, except I could never show you what's in row number 2. Yes?
Are we interested to recover all the entries correctly?
Yeah, that's a very good question. At the moment, that's what we're interested in. But you're pointing towards a very interesting direction, which is we're going to see the framework is I'd like to recover everything. And we'll see when it's possible and when it's not possible. But when it's not possible, then maybe you would like to determine which entries can be reliably recovered. And we know absolutely nothing about this. So it's a great topic. When matrix completion is not possible, what is possible? Nobody knows. So this row is unsampled, and of course I will never be able to guess what's in this row because there's no information about x2 in this matrix. And so to use a simple example, if I have the preferences of all users for all items, but except there's a user I know nothing about him or her, how can I make any predictions? I can't. Or in the SensorNet case, you have a sensor and you don't know its distance to anybody. How can you locate it? It's not possible. Okay. So the recovery is not possible. And of course, to kind of avoid silly discussions about showing you everything except like a row or a column or something like this, this is the only time we're going to use probability. We're going to assume that the entries are selected at random, that the entries that choose to reveal are selected at random. And not because I believe in probability, because I'm interested in describing what happens in most cases, but maybe not in all cases. Okay. So then we arrive at this conclusion, which is that, well, if we're lucky, if the matrix you wish to recover, the rank matrix is not of this kind, if I sample entries at random, I can hope that perhaps there's only one low rank matrix which is consistent with the sampled entries. Okay, so this is an only hope, and if I give you a subset of entries and I say how many rank 17 matrices are consistent with these entries, this is an NP-hard problem to decide. It's extremely difficult. Okay, but we can hope, we can dream that given the entries you gave me, there's only one low-rank matrix that would agree with this data, and therefore, if I were to minimize the rank of the matrix X, and I'm going to set up an optimization problem where X is a decision variable, I'm going to find for the matrix that matches the data you gave me and has minimum rank, and if there's only one low-rank matrix consistent with this data, I will find it. The problem with this is that it's NP-hard. So I know some of you are interested in compressed sensing, in L0 minimization. L0 minimization is very hard. It's combinatorial. But if you think L0 minimization is hard, think again, because rank minimization is even harder. I believe that the best algorithm we know to actually solve a rank problem under linear constraints is doubly exponential in the size of the matrix. What that means is that when it's 8, you cannot solve it. So we're going to do something else, and we're going to propose a heuristic. And the heuristic is to replace the rank functional by the nuclear norm, which is the sum of the singular values of a matrix. So let's introduce the nuclear norm. And the nuclear norm is simply, we look at the singular values of the matrix X, and the nuclear norm of X is simply the sum of the singular values of the matrix. It is not obvious that it is a norm. It's not something that is obvious. It's a summer school, so you can actually show that it obeys the triangle inequality, which is not a trivial thing. I'll tell you up front, it's not a trivial thing, but it is a norm. And in particular, because it is a norm, it's convex. And what I'm going to do is I'm going to try to minimize the nuclear norm subject to the data I have seen match. So I'm going to replace the rank by this nuclear norm. And in a way, what we're doing is a bit similar. Are people familiar with sparse recovery, like compressed sensing and the likes? How many people are familiar with this stuff? Quite a bit. Okay. So in a bit, what we're doing is a bit what we're doing in compressed sensing, where we'd like to minimize the cardinality. Or we can't, so we minimize the L1 norm instead. And here we do something similar. We minimize the nuclear norm subject to data constraints. Now, I would like to draw a picture. Another way this talk is different is I'm going to use a blackboard from time to time. So why is it that we use the L1 norm in compressed sensing or in sparse recovery? It's because, if I have sparse signals, which I can only draw in 2 dimensions. So I have sparse signals. So what is it to be sparse in 2D? It's like one component is not 0 and the other is 0. So here is 4 signals that have energy 1 and are sparse. Okay? And why is it that we use the L1 norm in compressed sensing? We use the L1 norm. We would like to use the L0 norm, but we can't. And so we're going to use the L1 norm because the L1 norm is a norm that is the closest to the L0 norm. And another way of saying this is that the convex hull of very sparse signals is precisely the L1 ball. And so the reason the L1, we should use L1 and not anything else, is because the smallest convex body that contains sparse signal is nothing else but the L1 ball. And so we should use the L1 norm for this reason. Now for this problem, it's impossible to draw, but something like this is happening. You can ask, what are the simplest objects I'm interested in? And the simplest objects I'm interested in are rank 1 matrices. And I could ask, what is the convex hull of rank 1 matrices? And it turns out that it's this nuclear ball, that it is a set of matrices with nuclear norm less than 1. And so for the same reason that the L1 norm is a tightest relaxation to the L0 combinatorial norm, the nuclear norm is a tightest relaxation, convex relaxation, to the combinatorial norm, which is the rank. Now another way of saying this is that the rank is of course counting the number of non-zero singular values. Right, so it's the L0 norm of the spectrum, and the nuclear norm is the L1 norm of the spectrum. Okay. Now this is an optimization problem that is convex because we have a convex objective and we have linear equality constraints. So it's a convex optimization program. In fact, it can be recast as a semi-definite program. That's something I have the right to talk about because this is something I can solve on the computer, at least in polynomial time. Now, you may not know about semi-definite programming. Semi-definite programming is a special class of convex optimization programs. I'm sure everybody knows about LPs. And in many ways, SDPs are the natural extension of LPs. And so an LP is the stuff we all know. We have a decision variable x, which is a vector in n dimension. And then LP is simply minimizing a linear function of x subject to linear equality constraints and a cone constraint which says that x is in positive orthant. And a semi-definite program, so what is an LP is minimize a linear function over a slice of the positive orthant. And what is a semi-definite program? A semi-definite program is, well, you minimize a linear function of x, but now x is, your decision variable is a symmetric matrix. And so you minimize a linear function of a symmetric matrix over with linear equality constraints and the additional constraint that x is positive semi-definite. And so it's exactly what you have as an LP, is you minimize the linear function over a slice, not of the positive orthant, but of the positive semi-definite cone. Okay, so that's a semi-definite program. And to show you that minimizing the nuclear norm is simply a semi-definite program, let's look at a very simple case. Let's assume that X, the matrix we're looking for, is a covariance matrix, so we know that it's positive semi-definite. So in that case, the sum of the singular values, if X is positive semi-definite, is simply the trace. And so I have a semi-definite program in standard form, since I'm minimizing a linear function of X subject to linear equality constraints and a positive semi-definite constraint. That's a semi-definite program in standard form. And it's a kind of a program that was proposed back in the literature on control by Mesbahi and Papavassilopoulos in the late 90s. In the general case, the nuclear norm has a semi-definite programming characterization. And I'm not going to give you all the details. I'm going to just show you that the nuclear norm, first of all, is a norm, and second, has an SDP characterization. And the way we do this typically is say that if I maximize the inner product between U and a matrix X subject to all matrices U with spectral norm less than 1, that is with maximum singular value is less than 1, I claim that this is X star. Okay? So what we're learning is that the nuclear norm is a dual norm to the spectral norm, which is a top singular value of a matrix. And because it's a dual norm, it's a norm. But that's not obvious, but let's assume that this is the case. Then is this a semi-definite program? Well, not quite, because I don't have a semi-definite program, a linear matrix inequality here, but I can turn it into an LMI by saying that I maximize an inner product between U and X, so the decision variable is U. subject to what does it mean for a matrix U to have norm less than 1. It means that this matrix with I, the identity on the diagonal and U star off diagonal is positive semi-definite. And so the nuclear norm, if you don't know how to calculate the nuclear norm of a matrix, you can solve an SDP. And this SDP is simply find the U that maximizes U dot X times under these constraints, which is an SDP. Okay, so that shows you that the nuclear norm has an SDP characterization, and that's useful. And that's something that has been recognized in Mariam Fazl's thesis. She was a student of Stephen Boyd. And so we all know, it's been 10 years that we know that the nuclear norm is essentially problems, convex problems involving the nuclear norm are indeed SDPs. Okay. All right, so let's go back to the theme of this lecture, which is the sampling of low-rank matrices. Here's another example of a low-rank matrix, which obviously cannot be recovered by a subset of entries. So here, let's say it's a symmetric matrix with eigenvectors E1 plus E2 over square root of 2, E1 minus E2 over square root of 2. It's a matrix that has some stuff here and then 0 elsewhere. And again, if I show you 50% of the entries, even though it's a matrix of rank 2, you will not know what this matrix is. To me, the most telling example of the difficulties in recovering low-rank matrix is this example. So in this example, we have a matrix of rank 1 whose first row is X and everything else is 0. So it's obviously a matrix of rank 1. And so it should be a very simple object. That is, its number of degrees of freedom is tiny. And so I should be able to recover it from perhaps a few sampled entries. But obviously, we can't. Because if you sample these entries at random, you're going to miss elements in the first row. And there's no way you can tell me what they are. What that's saying is that, of course, this row is orthogonal to every row. So if my preferences for movies is orthogonal to every, what is the idea of the Netflix prize? And the idea of the Netflix prize is to learn from the experience of others. That is, we try to predict Emmanuel ratings for movies, and there are people in the samples that look like Emmanuel, so I could use them to predict Emmanuel ratings. But here, if a row is orthogonal to every other row, it means that you have very special users that like movies like nobody else, and therefore prediction becomes impossible. Okay, so what we're learning from these examples, where obviously matrix completion is not possible, is that the row space and the column space cannot be aligned with the axis. That here we have a column space which is E1, and that's not good. Okay, because if we have a column space or row space that is aligned with the basis vector so that, for example, your matrix looks like a row or like a column, nothing can be done. And so we're going to try to capture this geometrically, and that's kind of the most technical slide I'm going to have. And the geometry is kind of simple. What we want to do to be able to kind of develop a useful theory of sampling of low-rank matrices, of data matrices in general, is we would like to have that its column space and its row space are not aligned with the coordinate axis. And one way to capture this notion is by a notion of incoherence, which for those of you who are familiar with compressed sensing should ring a little bell. So if I look at a matrix M, and let's suppose that it's square to make things simpler, and let's assume that U sigma V star is its singular value decomposition, I'm going to make an assumption which is essentially saying that the singular vectors of this matrix, or speaking as a statistician, that the principal components of this matrix, or we heard the term Karhunen-Love decomposition yesterday, that the principal component, the Karhunen-Love decomposition, whatever you want to call it, I'm going to make an assumption that these principal components are not too sparse. Because if the singular vectors or the principal components are sparse, as is the case here, because one principal component is E1, E1 is a singular vector, it's very sparse, then I can make matrices that look like this. If the principal components or the singular vectors are very sparse, or the eigenvectors, pick the word you're more comfortable with, are very sparse, then I can make matrices with lots of zeros, and sampling is going to become impossible. So we're going to make an assumption, and the assumption is going to be that the singular vectors U and V's are not sparse, and we're going to quantify this by a parameter which we're going to call mu, and that's the only parameter that the theory needs, is a parameter quantifying how sparse are the singular vectors. And the main assumption is right here. There's a technical assumption here which is far less essential, the main assumption is right here, which is that we're going to assume that the singular vectors are somehow spread around, that they don't put too much of the energy in few coordinates, which is that when I look at them one by one, the maximum component is mu over n, where mu is a parameter of interest. Okay, so graphically, when mu is small, what it means is that the principal components look like something like this. They don't look like this. Okay, they don't put all their mass on one movie or one user or one sensor or whatever. Okay, all right. There's a geometric condition which is easier, there's a weaker condition which is saying that when I look at a basis vector EI, I don't want the basis vector to project too well onto the column space or the row space. This is captured by this geometric notion that says that when I take a basis vector and I project it onto the column space, when I measure the correlation between a basis vector and the column space or between a basis vector and the row space, I don't want these basis vectors to be too correlated with the column or the row space. Okay, and so we need, intuitively, we need small values of mu to be able to say anything useful. Otherwise, as I said, we have matrices that look like this. Now you can ask, well, do random matrices have small values of mu? And absolutely. You can check, and it's not very difficult to show that mu is always between 1 and n. So mu is always between 1 and n, obviously. So mu is less than n and it's bigger than 1. It's less than n because this is a size of an entry of an orthogonal matrix. So uij has to be less than 1, which means that mu has to be less than n. And it has to be bigger than 1 because of the trace formula, which is a very simple exercise. So mu has to be between 1 and n. And so we're going to assume that the matrix is going to be called incoherent when the singular mu is close to 1 and very coherent when mu is close to n. Now, if you take a typical matrix and you ask what is the value of mu of if I give you a random plane, that is, I give you a random orthogonal matrix U and of dimension R, and I say what is the value of mu? Mu is essentially a constant, independent of n. So by that I mean most matrices are incoherent in the sense of this definition. Okay. All right, so now here's the first information theoretic result that we have, and it emphasizes this role played by the coherence. And so the result says the following, that if you show me m entries, but m happens to be smaller than this coherence parameter, times the number of degrees of freedom, so let's assume that the matrix is square to make things simple. So if the number of entries you show me is less than the coherence times the number of degrees of freedom times the log factor, there is no algorithm on earth that can recover this matrix. And so it's a very satisfactory result because it's a very tight result, something you cannot hope to improve too much. So let's look at this again. If the number of entries is smaller than this coherence parameter that is quantifying how spread the principal components are, if it's smaller than this parameter mu times the number of degrees of freedom in a matrix of rank R times the log factor, then no method whatsoever can work. Well, you can show, for example, that if you give me a random sample of set of cardinality m, no matter what matrix I have with coherence mu, I can find another one that exactly gives me the same data.
So it's just entry counting.
Yeah, yeah.
So you won't cover a row or a column if you're below this? There will be a row or a column that will not be covered?
No, because if the rank is high, for example, if the rank is very high, you would if the rank is n over 2, then you see at least n over 2 entries per row. Yeah.
Because you can always get the lower bound by saying if I don't touch a row or a column, then I'm definitely not.
Absolutely, and hold on to this because that's what I'm going to use to show you why this log factor comes in.
Do we have the assumption of mu to be constant?
No, mu is whatever it is. Mu is a parameter. You have seen the true matrix. You have calculated mu because you've looked at how well the column space and the row space are aligned. You have calculated mu, and it's whatever it is. But let me go back to your point, which is that if mu is of order 1 or like 2, then what it's saying is that roughly I need nr log n samples, and I cannot do with fewer. So even in the very best case where the matrix is highly incoherent, that is that its singular vectors are really spread, I need to see nr log n samples. I can't do with fewer. Okay. All right. So this is what is not possible. You cannot. This is a limit. This is an information theoretic limit. If somebody says, let's say the coherence is order 1. If somebody says, you know, I have an algorithm that reconstruct matrices from fewer than nr log n samples, you say it's not possible. This person cannot say the truth. Okay. Now, as I said, it's connected to what Alex was saying. It's connected to the coupon collector problem, and we'll see this in a minute. So this log factor has to do with some coupon collector effect. It has to do with lots of things, and we're going to see this in a minute. But before I discuss this result, I want to kind of, so here's a lower bound, and then we're looking for an upper bound. Okay. And the upper bound is this. So we have this proposal of seeing very few entries and guessing the entries that you have not seen by solving a nuclear norm problem. And the result is quite surprising. The result says that if we have this incoherence assumption, I show you a random set of entries of size nr log n squared, mu times nr times log n squared, then this semi-definite program that knows nothing about nothing will guess all the entries that you have not seen exactly and with no error. Right? So this is the upper bound of your sampling theorem. We know that we cannot have any algorithm that succeeds if it furnishes less than the coherence times the number of degrees of freedom times the log factor. And as soon as I have the coherence times the number of degrees of freedom times log n squared, then this semi-definite program, just minimizing the nuclear norm subject to data constraints, will fill out all the entries that you have not seen exactly as with no error whatsoever.
Can you specify what is random and what is not when you talk about it?
Okay, the only piece of randomness is, so this is a result that holds with high probability. Okay, and the only piece of randomness has to do with the entries I choose to reveal. So my model is I reveal entries, m entries chosen uniformly at random, and the result holds with high probability with respect to that choice. There's nothing else random. The matrix is deterministic. It's whatever you have. It's a Netflix matrix. It's a center matrix. There's no, I don't need to assume that the matrix itself is random. The matrix is fixed. What I decide to reveal is revealed at random. And if I reveal a number of entries, which is essentially degrees of freedom times this log n squared, then what I'm guaranteed is that this semi-definite program will fill up all the entries with no error.
So if the singular vectors are bad, are sparse, then mu will be order n.
No. If the singular value vectors are sparse?
Yeah, like the bad case you
yes.
said. So then this still holds, right? Because
yes.
But it will just, mu will be large, right?
Yes. So mu can be very large. Mu can be of size n, actually.
Okay, so then if it's n, then I have to basically sample n squared.
You have to sample n squared times.
Which is like
yeah, so it's really the minimum of nr log n squared. And
so there's no assumption on mu in this.
No assumption on mu whatsoever. So if the matrix is very bad, if mu is n, as in this case, what the theorem says is mu is n, and so you have, so here we have a random matrix. Mu is n for this matrix because there's one singular vector that has a 1 and then everything else is 0. So mu is n, and what the theorem says is you have to see n squared entries. Both the lower bound and the upper bound match in this case. You have to see everything. There's no way around it. And so, yeah. Okay. All right. So here's to me, it's kind of the surprise that you solve this convex optimization problem, and it recovers all what has been left unsampled, which is the enormous fraction of the matrix, actually.
When are they the furthest apart, the bounds? If you go to the previous page?
They're off by a log factor. Yeah, this is just a log n versus a log squared n. There's some claim in the field that we can bridge this gap, but it's a bit early to be sure. Yeah, so there's when I use this symbol, perhaps I should have made me precise. There's a constant we don't really know how to calculate. Right. There's a numerical constant. But yeah, it's on the order of degrees of freedom times the log factor.
On the last slide you showed so far, so R is all of 1. Where is the dependence of R? Is dependence of R on linear probability or?
No, it's in the number of measurements you need to see. The number of measurements is dimension times rank times the log factor.
But is it so R goes off 1, so that there might be some, let's say, exponential dependence on R somewhere?
Yeah. No, but it's not. There's no exponential. It's like, I think it's n. I think if you look at the proof, it's n r squared log n squared or something like that.
Okay.
Yeah.
Yeah.
Yes. By the way, this best result, the best result known today, is going to be published in the IT Transactions. It's a result due to David Gross, who is this quantum physicist who is doing these experiments I was telling you about. And a phenomenal paper, by the way.
Which direction does the community believe you can bridge the gap?
Oh, we believe that there's no log n squared.
There is no square.
Yeah, there's no square.
It should be log n.
Yeah. Well, they differ by a constant amount. But the lower bound and the upper bound differ by a constant amount.
But towards the lower bound.
Yes, absolutely. Yeah? Yes. Yes, it's perfect. Infinite precision. What I'm assuming in this first part is that you see perfect. Whenever I give you an entry, it's a perfect data point, and then there are entries you don't see. And when I'm saying that all you don't see, you guess it to how many digits of accuracy you want. It's perfect. Yeah.
What is the difference between the first statement and the improvement statement?
For all values of R with Terence, we were only able to show that there was degrees of freedom times log n to the 6. And here, David Gross was managed to put the 6 and transform into a 2.
This holds also for non-low rank. R could be.
Yeah, R could be large. I mean, of course. Yeah.
To what extent can the uniform sampling assumption be relaxed? I mean, can we have some?
I really love these questions because this is a second very good question. The first one, let me go back. The first one was, suppose I have fewer samples than this. So that was your question. Then matrix completion is not possible. But perhaps there are entries I can recover. That was question number 1, which I think is very interesting. Question number 2, which is equally interesting, is what if the entries are not revealed at random? And we know nothing. And these are 2 very good topics. Because in the center net case, they are certainly not revealed at random because the entries I choose to reveal depend on the distances. And so this assumption is violated. Yet when you do it on sensor nets, you do your simulation, you put sensors in a cube, you measure distances, you do this, it works perfectly. But it's not covered by what I'm presenting because it's the value of the matrix itself that decides whether you're sampled or not.
So another question I have, it's a general question. Many problems in this community network coding you can put in this framework in a finite field. So I give you a matrix in a finite field, I want to know, do you think any of this machinery transfers?
No.
It's completely different?
No, because it uses a lot of geometries. There's a special role played by the nuclear norm, which I don't see how it translates into a finite field. Okay. All right. So I'm running a bit out of time, which is not a bad thing because, I like to get questions, so it's not a bad thing. But we're a bit behind. Okay, so this is what I call the unreasonable effectiveness of convex programming. So why is this so you would like to minimize the rank, but it's combinatorially hard. You don't. And what the theorem says, if you look at it carefully as a computer scientist, what the theorem says is something cute. It says that, well, there's only one, first of all, what it says is under this condition, there's only one low-rank matrix consistent with the data, and you can get it by combinatorial optimization. But it's also said that there's only one solution to the nuclear norm minimization problem, and they are the same. So what you have is you would like to minimize the rank subject to data constraints. You can't. You minimize this convex functional subject to data constraint. And what you guarantee is they have the same solution, which is interesting because it says there's something which is combinatorially hard that you think you could not solve, but you can actually solve it in polynomial time. Of course, this equivalence does not hold everywhere, and if it were to hold everywhere, I would go and claim $1 million because then P equals NP. So it's only valid in a region. I want to mention results by my colleague from Stanford, Andrea Montanari, who has a different approach to matrix completion using spectral methods. And we're also, this group, Andrea and his student, we're also able to obtain very impressive results using algorithms that have nothing to do with what I've presented. And this is also published in the Transactions. There was an important paper by Benjamin Resch, Pablo Perillo, and Mariam Fezel in 2007 in a very different setup, which is essentially like a compressed sensing setup where the measurements you acquire about the matrix are so randomized that you essentially hit the matrix against another random matrix. And then I mentioned that some of this work was joint with Ben. With Ben, we could not prove the nice result you've seen here. We were off by quite a bit. We could prove that if the number of samples was greater than n to the 1.2 r log n, not n r log n, we could do well. And of course, now this became n log n. Okay. All right. So there's quite a bit of work in the field about these things. And so the literature, as I said, is rapidly growing. So in the last 5 minutes of this first part, I'm going to try to explain to you why is it that we need this log n. So I'm going to try to explain it very simply. And it's following the ideas that Alex just mentioned, which is that if you give me a matrix of rank 1, the theorem says that I need to see n log n samples. Right? So, so if I have a matrix of rank 1, then you instantiate the theorem, and the lower bound says, I need to see n log n samples. And why these log n samples? Why do we need to see n log n sample? Well, it's connected to this coupon collector problem. And the coupon collector says what? You reveal entries at random, and then we're going to put a star in a row that has been sampled, and no star when the row has not been sampled. And I've explained that, of course, if you want to do matrix completion, even though the matrix has rank 1, you need at least 1 star per row. And so you can ask, whenever I sample a matrix, how many samples do I need to take to make sure that I have sampled every row? And you can see that who is familiar with a coupon collector? Yeah, so coupon collector is like you have a list of items. Like when I was young, we had like images of soccer players, and you would go to the bookstore, and then you would buy images in a little pocket, and you would open the thing, and then you would stick them in an album. And the question is, if each time you draw an image at random, how many images do you need to purchase before you finish your collection? And that's a coupon collector problem. And it's well known that it's about n log n trips to the bookstores you have to make. You have to collect n log n samples. And so here it's exactly the same thing, because each time you pick a row at random and you put an observation in that row, and how many entries do you have to sample until at least every row is sampled, it's at least 2n log n. So you can see that with n entries sampled at random, there's no way you can actually sample every row. And so that's why that explains this log n in the lower bound. There's more, for those of you who care about graph theory, and some of you do, there are more sophisticated implications of this result. So I'll just mention one cute one, which is you can construct the bipartite graph. So so here are the nodes corresponding to the row indices, and here are the nodes corresponding to the column indices. And what we're going to do is we're going to construct a bipartite graph where I'm going to collect a row index to a column index if and only if the entry ij has been observed. Okay, so this is a bipartite graph. Okay, and so this bipartite graph, we're going to be interested in the number of connected components of this bipartite graph. And in this case, I show you 2 entries, and how many components I have? These two guys, I have 4 components. And I said that this bipartite graph is not fully connected, even though I'm giving you a matrix of rank 1. Matrix completion is not possible. And why is it the case? It is the case because suppose we have 2 components and not 1. We have 2 connected components, but no connections in between. Then when I reorder the column and row indices, when I just do a permutation of the row indices and column indices, I have entries in this first connected components. I see entries in the second connected component, but nothing off diagonal because the components are disconnected. And I say, if I have a rank 1 matrix of which I see nothing off diagonal, no method can succeed. Okay, so it's not trivial to prove this, but I'm just going to do it by an example. So here's a 2x2 matrix where I see stuff on the diagonal but nothing off diagonal. And I say, can this be a rank 0 matrix? Yes? No. The only rank 0 matrix I know is a 0 matrix, and that's difficult. Can it be a rank 1 matrix? Yes. How many rank 1 matrix can it be? 1? All these matrices are of rank 1, and there's no way you can tell me the value of this element. Absolutely no way. Okay? And so this kind of shows you via an example that if you see nothing of diagonal, even though I'm giving you a very simple rank 1 matrix, there's nothing you can do. All right, okay. On the other hand, so now we're going to take a break in 1 minute. On the other hand, why is the theorem working? So what the theorem is working is, so what this stuff is not displaying, which is a bit of a problem, because in the second part of the talk I have so many images to show you, because this has surprising applications in image processing. So, okay. Well, do you see a cylinder here? Yeah. Okay. All right, so what is this cylinder? The cylinder is the set of matrices that are symmetric and with nuclear norm less than 1. That's a nuclear ball plotted in 3D. And now what you have to show is that, of course, you have a feasible set, which is a linear space. And of course, the solution to your semi-definite program is actually going to be the location where this is tangent to this nuclear ball. And what you want to show is that it's tangent at the right place. And why is it tangent at the right place? It's tangent at the right place because it so happened geometrically that the extreme point of these convex sets are low-rank objects. Just like the extreme point of the L1 ball, why is it that L1 works why is it that compressed sensing works? Compressed sensing works because if you have a one sparse vector, a vector which has only one non-zero components, and you make only one measurement, then after measurement you know that the guy is on the line. And now you say, okay, on that line, what is a guy that has minimum L1 norm? And this line is touching the L1 ball at one of its corners. And that's why compressed sensing works. That's why you recover sparse solutions by L1 minimization. And here it's kind of the same thing, is that the extreme point of this very difficult convex body corresponds to low-rank matrices. And so this feasible set is touching the nuclear ball. At its extreme point, it happens to be low-rank object. And that's essentially why it works. It's because the nuclear ball is pointy around low-rank objects. Yes?
Regarding the green and log n samples, so I mean, if we just randomly visit each row, and then whenever we visit a row, we don't visit again, then in that case,
no, because you remember you need this gigantic. You need to make sure this graph is fully connected. You need a lot of stuff to be able to do matrix completion. Sampling per row is not sufficient. One entry per row is far from being sufficient, because then this guy is not fully connected. You need. By the way, for those of you who care about spectral theory, how many edges? If you draw edges at random, how many edges do you need to get a fully connected component? N log n. That's a beautiful result due to Erdos. N log n edges, and then you guarantee to have a gigantic component. I mean, a fully connected component. Okay, all right. Then so the proof is very difficult because, the proof is very involved. It's a very deep issue. It's all probability. It's a topic in probability theory. It does not invoke anything else. What you have to show is that you have to show that this random plane, it's random because this plane is determined by the orientation you decide to reveal. So it has a random orientation. This random plane is tangent to the nuclear ball at exactly the right point. It's a probability question. It's only a probability to show that this happens. And that's not trivial. Okay, so maybe I'll take a quick break, and then